Okay, hi everyone. Now that we have some kind of grasp of galaxies, we should talk about how those galaxies change over time. So, the time scale of galaxies is billions of years. There is no way for a human to watch a galaxy's life from start to finish. But we can observe galaxies at different cosmic distances that correspond to different, what we call look back times, or how far back in time we can see the galaxy. We can look at the properties of galaxies at different look back times and get a sense of how galaxies evolve. Some of the properties we want to look at are galaxy spectra, color, and morphology, right? Shapes. So the distance to a galaxy can be derived from its redshift, or how much the spectral lines are shifted due to the expansion of the universe. This also depends on some properties of the universe, which we will not go into. Using the currently accepted model of the universe, our best estimate for the age of the universe is 13.8 billion years old. Astronomers measure the redshift in the galaxy spectra, use the Hubble constant and a model of the universe to find distance, and use the distance and constant speed of light to infer how back or how far back in time we are seeing the galaxy, right? We're inferring the look back time. We can also use the Doppler shifts in the spectra to tell us how fast the galaxy is rotating and how massive it is. We can't get spectra for every galaxy, though. In fact, most galaxies look too dim to us to actually get good spectra. But we can look at the overall color of a galaxy to get a rough estimate of the type of stars a galaxy has. If we see a lot of blue, that indicates young stars and relatively recent star formation. If we don't see blue stars and instead we see a stellar population that's dominated by the light from yellow and red stars, we know that there is mostly old stars in this galaxy and that there is no current star formation. We can also see if there is any evolution of galaxies by counting the relative numbers of spirals and ellipticals at different look-back times. We know that spirals have more active star formation than ellipticals, so by counting the relative numbers of each, we can get a sense of how much star formation was going on in the universe at different times. So galaxies are made of stars, and nearly all galaxies have at least some old stars in them. For example, there are stars in the Milky Way that are 13 billion years old. So if we assume that the Milky Way is as old as its oldest part, then the Milky Way is at least 13 billion years old. What's pretty interesting is that we have seen ellipticals at about half the universe's age have some pretty old stars. Those stars must have formed billions of years earlier than our observations. Ellipticals as a galaxy population don't seem to have changed much since the universe was 6 to 8 billion years old. But we've observed galaxies even earlier than that. We've seen galaxies from less than a billion years after the Big Bang, and they already have elements that must be produced in stars and scattered when those stars die. So this implies that there was an entire generation of stars that lived and died less than a billion years after the Big Bang. And so these are the population 3 stars that I talked about a week or so ago. We've also noticed that galaxies in the early universe don't look the same as modern galaxies. We've observed galaxies from when the universe was about 3 billion years old, and they are very blue with higher star formation rates than nearby galaxies and smaller and less massive, so about 1/20th the mass of the Milky Way. So we may be seeing seeds of quote unquote adult galaxies. And on your screen here, this is what galaxies tend to look like at different look back times. And you can see kind of earlier in the universe's history, which kind of is this area here, these galaxies look very different from the galaxies in, more modern times. So the main point you should get from this is that galaxies change over time. It may be slow, but at different epochs, we can see they look different. We can see that with our eyes. Their star formation rates change. Um, they grow in mass and they grow in extent. So, what are ways in which galaxies can change? Like, how do they do this? So, a big way galaxies can change is through galaxy mergers. So galaxies collide. We've kind of seen this process happening. Stars tend not to collide with each other, but their orbits can be disrupted. This process can take hundreds of millions of years to complete, but because it disrupts the orbit of stars, that means that kind of the whole shape of the galaxy can change when they collide together. So your book defines a collision of galaxies that are roughly the same size as mergers, and the collision between a large galaxy and a small galaxy to be galactic cannibalism, since the larger galaxy doesn't tend to get too distorted, just kind of absorbs the smaller galaxy. I think more often we call the mergers between galaxies that are approximately the same size as a major merger, and the mergers between galaxies, like a large and small galaxy, are called minor mergers. So, very massive elliptical galaxies are likely formed via a bunch of minor mergers. So, these smaller galaxies being kind of absorbed by larger galaxies. If a galaxy has a lot of gas, this gas can be compressed and trigger a starburst, which is just kind of a limited time of very intense star formation. Our observations indicate that galaxy interactions were much more common billions of years ago. And on your screen here, is there are examples of kind of what these look like. This would be a major merger. These two galaxies here are roughly the same size. And right here, this is a big galaxy. I believe the galaxy, this might be this one right here. It's much smaller than the galaxy it's merging with. Something else that can impact the star formation in galaxies is the presence of a quasar or an active galactic nucleus, or an AGN. So AGN and quasar are often used interchangeably. I'll probably mostly use AGN. Um, and AGN is a supermassive black hole in the center of a galaxy that is surrounded by an accretion disk. The matter in the disk heats up and shines really bright, sometimes brighter than the entire host galaxy. This can also produce jets. So on your screen, this is an AGN blasting out jets in this kind of above and below, kind of this kind of disky area. And these jets can accelerate particles out of the galaxy and can disrupt gas clouds. And this can interrupt star formation. So the jets are flinging out what would normally be fuel for star formation, and it's breaking up gas clouds that would have been actually really nice places for star formation to take place. So AGN, when they're kind of turned on, um, when the gas starts to get heated up and fall in and produce these jets, can really interrupt the normal star formation process in a galaxy. Okay, so important to interpreting the universe is something called the cosmological principle. So Hubble, when he was doing his work, he counted the galaxies he saw in many different directions and found basically the same number. So we say that the universe is isotropic and homogeneous. And basically that means that at large enough scales, the universe is basically the same everywhere you look. This is kind of just a schematic of how that might have worked. So here we are at Earth. We look in one direction, we see a number of galaxies. We look a different direction, we see basically the same number. And this is kind of what Hubble did. He did this for many, many different regions of the sky. He couldn't do the entire sky. Um, but he basically found that he saw the same thing everywhere he looked. So this is important for our understanding of the universe. If we didn't think the universe looked pretty much the same in every direction, it would be hard to make predictions, right? If our neighborhood was unusual in some way, it would be hard to extrapolate to other areas. So the cosmological principle, it's based on, observations, but it is kind of an assumption in cosmology, and it does seem to work. Okay, so let's talk a little bit more about kind of the universe as a whole and how the galaxies in it evolve by talking about kind of our neighborhood here. We'll start close to home. The Milky Way is part of a small group of galaxies that we call the local group. There are about 60 members, mostly faint dwarf galaxies spread over 3 million light years. The main two members are Andromeda and the Milky Way. So on our screen here, kind of how this local group is laid out with the Milky Way up here, Andromeda down here. Um, so half of the mass of the local group are in the Milky Way and Andromeda. They are by far the biggest galaxies in this group. They dominate this group. There are larger groups of galaxies called galaxy clusters. So a rich cluster can have tens of thousands of galaxies in them. The Virgo cluster is the closest cluster to us, about 50 million light years away. It has thousands of members. This is a portion of the Virgo cluster here. As you can see, there's many bright, what are probably elliptical galaxies. The Coma cluster is another very well-studied cluster. It is enormous. It's about a 10 million light years in diameter. It's about 300 million light years away and contains um, up to 30,000 galaxies. It is a little bit hard to tell sometimes, but this is a portion of the Coma cluster. The Coma cluster has two really big galaxies in the center of it. So galaxy clusters tend to have elliptical galaxies near the center with spiral galaxies near the outskirts. And both of these pictures here are kind of favoring looking at the cluster towards the center, especially the Coma cluster. And you can see um, almost all of these except for, something like this is a galaxy. And you see a lot of elliptical galaxies. Spiral galaxies tend to be at the edges of galaxy clusters if they're there. The dense center of a galaxy cluster is actually a really great spot for mergers to happen. Um, so when spiral galaxies are involved in a major merger, they often lose their spiral structure. So this could be a reason why we don't see many spirals in the center of clusters, because maybe a spiral galaxy falls into the center, and undergoes some sort of merger and they lose their spiral structure. They become an elliptical galaxy. The universe has kind of a honeycomb or Swiss cheese type shape. We have these filamentary structures called superclusters, and there are also vast, nearly empty spaces called voids. So the voids really are very empty. About 90% of galaxies live in about 10% of the volume of the universe. And this is a schematic of kind of how the universe how gravity has worked in the universe. You can see, supercluster areas. Up here is a map of galaxies created by the Sloan Digital Sky Survey. And you can see these dense areas where there's lots of galaxies, and you can see the dark areas are essentially just truly empty space. There's nothing there. Galaxies, because they're very massive and gravity works, they like to live together. We can't really talk about the evolution of galaxies without talking about dark matter. Um, we know that at least all pretty large galaxies sit in the middle of a dark matter halo. So understanding dark matter is pretty important. Um, it makes up most of the galaxy mass. It's pretty important, but not really evenly distributed around the galaxy. We don't see any evidence of dark matter in the solar system because we don't see any deviations from predicted orbits. All planets are orbiting as expected from Kepler's third law. The solar neighborhood is a little bit of a different story. So if we look at the orbits of stars that are about 100 light years from the sun, we do see some deviations, and those deviations indicate that about half of the mass in that volume of space is dark matter. We've seen evidence for dark matter around galaxies from our discussion of the Milky Way, but just to remind you, the orbits of stars in the outer part of the galaxy are faster than what we'd expect from Kepler's third law, which from this equation on the screen indicates that there is mass that we can't see. Remember, the orbits we expect from Kepler's laws is this red line right here, kind of slopes down, but what we see is something flatter called a flat rotation curve. Dark matter is also a really big deal in galaxy clusters. So how do we know? We still can't see dark matter. Um, well, we can measure the amount of dark matter in much the same way we did in the solar system, in the solar neighborhood, and in individual galaxies. We measure the velocity of galaxies orbiting the center of the cluster. See, you've got thousands of galaxies, and they're all whizzing around on an orbit that behaves according to Kepler's third law. What we find when we measure those orbits is that there is about 10 times as much dark matter as luminous matter in galaxy clusters. There are other ways too to measure dark matter. First, we can measure how much the gravitational force from a cluster is slowing down how fast other galaxies are moving away from it. So, for example, the Milky Way and other local group galaxies are lying on the outskirts of what's called the Virgo supercluster. The mass concentrated at the center of the Virgo cluster exerts a gravitational force on the local group. The local group is still moving away from the Virgo cluster due to the expansion of the universe, but gravity is slowing that down just a little bit, but enough to measure. We can compare our measurements to what we think should happen from Hubble's law and get an estimate of the amount of mass in the cluster. There are also methods or one method in particular called gravitational lensing. So matter bends spacetime and light follows that bend. And dark matter also bends spacetime. Sometimes astronomers can look at a massive cluster and kind of see like an arc of light. These are lensed galaxies from behind the cluster. Their light has been bent by all of the mass in that cluster. Astronomers can calculate how much matter is in the cluster based on how the light is distorted. This is a schematic of kind of how that works. So we have this cluster in between Earth and the galaxy we are trying to find. The light comes, towards Earth, but it is bent by all of the mass, and so it takes kind of a different path. And we might get something that looks like this. This is a real image down here. This galaxy would have been distorted like this here. So this is kind of all one galaxy, um, but its light is bent in such a way that it makes this arc. And every once in a while, you get things situated, like the geometry is just perfect, where you get just a complete circle around the galaxy or around the galaxy cluster, and that is called an Einstein ring. They're relatively rare, but they're pretty cool. But we can use these distortions to figure out actually how much mass is in the galaxy cluster. Finally, we can look at X-ray emission from galaxy clusters. So stars don't emit much in the X-ray, but hot gas does. So in clusters, there is a lot of gas moving around between the galaxies. Call it intra-cluster gas. Um, and the more mass is in the cluster, the faster the gas moves. So the faster it moves, the more it heats up and emits X-rays. And so we can use X-ray emission in this way to figure out how much mass is in the galaxy cluster. Compare that with how much mass we think is in normal luminous matter. The difference then would be dark matter. So we don't know what dark matter is, um, but we do know that dark matter and luminous matter are closely associated. There doesn't seem to be much dark matter in voids, for example, and there's not much regular matter in voids either. If we want to include dark matter in our mass to light ratio calculations, um, we would see a mass to light ratio of 100 or more, which would really indicate a substantial amount of dark matter. Theorists have come up with different types of dark matter that have different properties. They can generally be categorized as either hot or cold dark matter. This doesn't have anything to do with their temperature. It has to do with how fast the particles move. So hot dark matter moves fast and it doesn't let regular matter clump up to form small galaxies as efficiently. So cold dark matter moves slowly and lets matter form little clumps, right? Because matter and dark matter, they will interact only gravitationally. So if we have dark matter moving slowly, it kind of allows gravity to work on the regular matter and we get clumps of regular matter that eventually form stars, that eventually form galaxies. So most of our observations right now favor cold dark matter over hot dark matter. So we think that by and large, galaxies form where there are little clumps of dark matter. Gravity and the dark matter draws in normal matter, and over time we get a galaxy. But how do galaxies grow? So there are a couple of different ideas about how they kind of form and grow. And one is either it's rapid collapse, or also I learned it as monolithic collapse, and then environmental effects, which has also been called hierarchical merging. So rapid collapse is when a galaxy basically formed all at once. Environmental effects or hierarchical merging is when galaxies collide and merge over time. So there are very massive elliptical galaxies that we have seen in the first billion years of the universe. So not really enough time for a bunch of small galaxies to merge together. So these galaxies actually probably did form kind of all at once with this rapid collapse or monolithic collapse. However, there are very, very massive, very giant ellipticals that are actually pretty rare before 6 billion years ago. These probably formed via merging. Um, they are more massive than the ellipticals in the early universe and have had time to merge with other galaxies. Spiral galaxies are a little bit different. Their bulges probably formed early, the disks probably formed later. So star formation in these galaxies were about 10 times higher 8 billion years ago. So it's kind of like spiral galaxies are going through kind of a slow motion rapid collapse, if that makes any sense at all. Okay, so the last thing I want to talk about is how we get large scale structure to begin with. So I showed you a few slides ago. The universe has kind of this Swiss cheese honeycomb shape. Um, there's evidence for these concentrations, these filaments, clusters, superclusters, and voids in the universe when it was 3 billion years old, which is relatively young, considering that we think it's about 13.8 billion years old now. So things were much hotter in the early universe, and we think that dark matter seeds in this hot cosmic soup grew by gravity into larger and larger structures. So the theory goes like this. Hot gas was perhaps vibrating, which may have concentrated matter into high density peaks and emptier space. So it's kind of what this is trying to illustrate here. So we have kind of a general, kind of a smoother distribution of dark matter, but the vibration caused these little peaks. And empty space kind of in between. So as the universe cooled, these peaks were kind of quote unquote frozen in. And this is where galaxies formed. Like after we have these tiny little slight overdensities, galaxies formed in this area as the universe cooled down. Okay, so that is about all right now for the evolution of galaxies. Remember to read the chapter, take the quiz. Let me know if you have any questions.